تشيك مايك. الرجاء من السادة الحضور التوجه إلى القاعة الرئيسية حيث ستبدأ جلستنا التالية. Ladies and gentlemen, please proceed to the main hall as our next session is going to begin. الرجاء من السادة الحضور التوجه إلى القاعة الرئيسية حيث ستبدأ جلستنا التالية. Ladies and gentlemen, please proceed to the main hall as our next session is going to begin. Check mic.
Check sound.
ندعوكم الآن لمتابعة الجلسة التالية للقمة تحت عنوان قفزة نوعية رسم ملامح مستقبل الحوسبة الكمية.
Welcome back, ladies and gentlemen. We hope you're looking forward to the next few sessions. We will now commence the fourth or fifth session titled Quantum Leap, the Future of Computing.
يقدمها مارك أوريغان المدير التقني لمنطقة أوروبا والشرق الأوسط وإفريقيا في شركة ديل للتكنولوجيا.
This session is presented by Marc O'Regan, CTO EMEA from Dell Technologies. Please welcome on stage.
Thank you. Thank you. Good afternoon, everybody. My name is Marc O'Regan. I'm the Chief Technology Officer for Dell Technologies for Europe, Middle East, and Africa. And yes, they put the Irish guy on stage to talk with you about quantum computing right after lunch. So if that doesn't give you indigestion, I'm not sure what will. I would like to begin by thanking the Foundation for inviting me to talk here. Very, very honored. And today I will speak with you about the future of where we see at Dell Technologies computing going, in particular quantum computing and its relationship with what we call classical or traditional computing. So I'd like to begin with a little parable. If I may, and that parable is about an emperor, a Chinese emperor who rewards a sage for doing extraordinarily important work. And he says to the sage, "Pick anything in my kingdom and I will give it to you." And the sage says to him, "What I would like is a grain of rice on the first square of a chessboard, and for that grain of rice to be multiplied by the square of 2 for each square on the chessboard." And what the emperor didn't realize was that by the time we reached the 64th square, there were more grains of rice on the chessboard that could fill the Pacific Ocean. It was that great. And when I think about this parable in computing terms, I believe as a technologist that we are fast approaching the 32nd square of that particular chessboard. We are starting to run out of horsepower and out of energy to solve some of the bigger problems of our time. What we call the wicked problems, problems around pollution, problems around population, problems around energy efficiency, problems around health, problems related to the citizens of the world, and even related to universal matters. The world we live in has been built on binary constructs, zeros and ones. And when we look at the world we've lived in, we look at our banks, our healthcare organizations, we look at our societies, we look at our cities, we look globally at how we've actually constructed the world we live in. It's based on binary computations, on zeros and ones, on yes or no's. And we've done very well in that regard, but as we move into a time where we want to explore solving greater problems, universal problems, we need to move towards a different type of technology that can help us solve for these types of problems. And what we've done at Dell is partnered with some of the world's best and brightest in this field in order to help take this capability forward and put it in the hands of the people who will use this to solve for problems within their industries, within their domains, and even for the citizens of their regions or their countries. And those people are you, the policymakers, the business owners, the organizational leaders who are responsible for looking into the future and solving for these and many, many other technology problems that we are looking to solve. Now, as we do that, we take teams of people with great ambition and great skills with us. But these are people who understand this binary world. How do we take them with us and create a relationship with that classical architecture and the data associated with that classical architecture, and make that relationship bound to, quantum physicists or quantum engineers, and so on and so forth. So our CEO at Dell talks a lot around innovation and building innovation and putting that innovation into the hands of the people that matter. Another quote that I specifically like is one from this guy here, Peter Drucker. He's a philosopher and he's an educator, and Peter Drucker talks about predicting the future, and the best way to actually predict the future is to go and build it. And that's exactly what we have done at Dell Technologies. We've built a capability where we can look at the compute architecture that we are familiar with at the M&O, machine operations layer, management and operations layer, and blend that architecture with the architecture associated with quantum systems. Now, our global CTO, John Rose, developed a vision for the technology world that he called the Strategic Six, or the Strat Six, and you can see them in no given order here. Edge, the real world, the cities, the hospitals, the ICUs, the endpoints, whether they're pumps, actuators, sensors, cameras within smart cities, or indeed whether they're people themselves. Artificial intelligence and AI functions being able to actually measure, do computations against specific problems in these edge domains and in these local domains. 5G management, the management of data as it comes into an ecosystem and flows through that ecosystem across cloud-native architectures, which is that new infrastructure, and then how we actually secure that event and build a level of trust into that event. So there's a number of mega trends that we noticed happening over 15 to 20 years. One of them is that this idea of computing reaching a near ephemeral state. What that means is computing is getting easier to build, easier to manage and easier to scale. There's also this idea of data exploding. If we go back simply 7 to 10 years, most of the data that we would have been working with is structured data. Today we're interested in structured data, semi-structured data, unstructured data, particularly in the world of artificial intelligence. And what this really brought to us was a distributed architecture shift, if you will. So, within that Strat 6, there are what we call substrats. And one of those substrats, you can see them all here, is quantum computing. And our interest in quantum computing is looking at simulating a quantum system and introducing that, as I mentioned a little bit earlier on, to organizations like your own. So in order to figure out where we are going, it's always a good idea to look back at where we've kind of come from. And if we look at the history of computers, we can go back many, many years into an era whereby we would have started out with mechanical computing. So this is what we would have called differential adder. That soon became, or leaned into, vacuum computing, which brought us up to a time when, in the recent past, when we would have had silicon. So this is really, general purpose CPUs demoted to a peer architecture. Today we're moving into this area that Albert Einstein called weird science. And we'll talk a little bit about that. And that area is interested in quantum mechanics and applying the laws of quantum mechanics and quantum physics into the architecture of computing. So when we think about a quantum computer, what do we think about? Well, this is a very basic example of a quantum computer up here. A quantum computer is very, very specific in the sense that it requires a very unique state in order to exist and in order to do the computations in a way that will produce value. So a typical quantum computing will be presented to you in its cryogenic state, which means that the temperature within the quantum system fetches as low down as 469 degrees minus Fahrenheit. So it's that cryogenic state that I mentioned a little bit earlier on, and within the quantum system itself, we're not dealing with data and binary constructs at all. We are dealing with particles, with atoms. And so the atoms bounce around this quantum system and do so quite comfortably until you start to introduce other atoms, where they start competing for space. Now, we'll get back to that competition for space and the relationship between the atoms in a moment's time. But what's really, really interesting here is when we look down into a compute system, we have what we call QASM, which is the quantum assembly language. And that QASM talks down into a control processor, into a control and measurement plane, what we might refer to as a data plane, which is on point 3 here. So we have control, we have measurement, we have control planes and processors, we have that environment isolation that I spoke to a few moments ago, and we have a quantum data plane. And what we can say and safely say about a quantum computer is that quantum computers rely on classical computers for information. And what we're interested in is synergizing the relationship between quantum systems, as I said, and classical systems, so the quantum system can manage the classical compute architecture and can pull from the quantum system some information or some data around a problem that you're trying to solve or an opportunity that you are trying to build out. So we talked about binary zeros and ones, and then we've talked about quantum states, or what we call qubits. Now, there's a couple of interesting things about quantum computers that we observe. One is that I could have a coin on my thumb, and I flick that coin into the air as it spins, I can ask any one of you in the audience what state that coin is in as it spins. Is it in a state of heads, or is it in a state of tails? Binary will tell you one or the other. Quantum will say that it is in two states at the one time. So this symbiotic state that quantum offers to us is exactly the computational efficiency and quality that makes quantum exciting in terms of solving problems. So that's one phenomenon. The second phenomenon is this idea of entanglement. So if I have an atom in this room, in my palm of my hand, and there is an atom that is entangled, that is connected to another atom or particle behind the surface of Pluto, for example, and that atom twitches 3 times, this atom will twitch 3 times also. It raises a number of different interesting things around what Einstein spent his entire career studying in terms of relativity, around time, around space, and around how we can solve for some of these problems in that regard. So we believe that superposition and entanglement is key. Because when we think about it, you look at a human, for example, a human construct is completely and utterly unique at all times. You know, we're made of, neurons, electrons, the content of our body, how we move, the configuration of our body is in consistent flux. It's in consistent movement. And when you think about this room and everybody in this room, there will never again, at any point in time, be a configuration like the configuration between us in this room. So that's really one way of thinking about how complex it is to solve a quantum problem and how much we rely on superposition and entanglement, relationship between the different atoms, and how that plays in to the computing element of quantum. So from a computing element of quantum, we have our classical computation sitting over here, and we have our quantum simulation over here. This is to say, we do not believe that quantum computing will replace at any time classical computing. Quite the opposite. Our opinion is that quantum computing will rely on classical computing in order to interpret what it is that you are trying to solve for. So there will be this symbiotic relationship between quantum and classical, and that relationship will continue to go on. So as a leader, as a policymaker, as a visionary for your organization, your respective organizations, we would recommend that you look through the lens of 2 eyes. One eye is on vigilance, and the other eye is on visioning. From a vigilance perspective, observe what the ecosystem looks like today and where that ecosystem is moving to. Implement with a plan. Think about what quantum technologies and architectures, computing, networking, any sort of post-quantum problem potentially that you're looking to solve for. For example, if RSA is cracked, and there has been soundings that it has been cracked, or is about to be, elsewhere in the world, well then, that's something that everybody in this room, everybody in this country, everyone in this world is going to be extraordinarily concerned about. So we need a technology that can respond to that, and that technology needs to be integral, it needs to be quick, and it needs to be extraordinarily accurate. And that is what quantum computing brings to the table, and that's how important quantum is for the future. So implementing it to solve for your own possibilities is something to think through from a vigilance perspective. Initiating it means trusting a partner who can take you into that world in a meaningful way, in a way that doesn't take you from, ice to fire, that actually takes you into that world with the teams that you know and trust and understand, who use the technologies that they know and trust and understand, and then selecting the right kind of use cases, the right kinds of technology, and the right team of people in order to be able to execute against that. From a visioning perspective, you have choice, so you have different choices of what type of quantum architecture you use. You have an inside-out and outside-in analysis in the sense that you will look into your own organization, you will see where the skills gaps are, and you will fill those skills gaps, like I mentioned earlier on, with partners. You will spotlight an architecture or an opportunity, and you will then you will map your quantum platform to that. So last year alone, I did 3 trips to this region. All 3 of them were with high-performance compute customers of Dell who were interested in looking into this world. And the springboard, if you will, or the platform from which they could actually spring into a quantum system was in their hands. It was the HPC system that they already owned. And that was the starting point for visioning for these particular customers. So the teams that we talk to, there's 3 of them. There's quantum specialists. These could be quantum physicists. These could be quantum engineers. This team will look at the most promising use cases that are specific and meaningful to you. They will work, or should work, with data scientists. These are people who understand mathematics and mathematical functions, where to map those functions to, and how to blend algorithms in order to do that, in order to extract information from data. And those teams will work with software developers, and we all know what software developers do. So imagine a world where you are trying to solve an optimization or a scale problem, and you used a quantum scientist or a quantum physicist to execute into a quantum system, pull the information back into a binary architecture, have that information compiled by a data scientist and delivered up into the CI/CD pipelines of a developer. So you can actually execute across your domain into your industry. That gives you huge power to differentiate yourselves against your competition, but also to solve for critical questions that you're asking within your own organization. So, I mentioned earlier on there are a number of different ways, like many technologies, to intersect with quantum. These are just 2. There are what we call trapped ions, or trapped qubits, and then there's superconducting qubits. So the trapped qubits, they have their features and they have their challenges. Each qubit is identical, it's the same as each other. It comes with long memory, so you second-long memory, but the clock speeds tend to be a little bit slower than other technologies. Superconducting qubits have really quick clock speeds, but they're not as reliable as trapped ions, or at least not yet. Things are getting better. Last week, IBM announced the release of their R2 Heron, which now takes us up to 156 qubits on their system. It's the biggest qubit quantum system on the planet today. This time 5 years ago, we were living in a world with 7 qubits. That was the biggest. So it was either 7 or 8, I can't remember, but it was in and around that area. So what do Dell do? So our interest, as I mentioned earlier on, is putting this into your hands. So we see a world where we have an input layer, an output layer, and a quantum layer. So we input information. That information goes into the quantum processor, as we described, and then we pull an output from that as well. The white illustrations here talk to classical infrastructure and classic electronics, whereas the black and dark gray areas denote the quantum systems. So we have compute, we have network, we have data storage capabilities, we have host processors and co-host processors, accelerators, GPUs, connecting into what we call QPUs, quantum processing units, or even virtual QPUs, so fractionized quantum processors, which then talk down into the control plane of the quantum system and give back the output of the query that went in initially back out to a classical compute architecture system. So in that space, there are three things really that we have written up and made available to the industry. And these are all available on the open source platforms, Git, Dell Quantum Hub, and so on and so forth. The first of this is an infrastructure as code architecture. This is a software package, if you will, that looks at what developers and data scientists, what tools they use daily. And working together with IBM and with other organizations, what we've been able to do is look at these technologies and package them up into a familiar architecture where a data scientist or a data engineer or a developer themselves can actually get in through Jupyter Notebook and then interface with a quantum system using the framework of choice. It could be TensorFlow AI framework, it could be PyTorch AI framework, and then orchestrate the event down onto the technology architecture. So taking a K8 or even a K3, a Kubernetes orchestration event, and pushing that down into the quantum system. So we've taken that, we've written it into a package, we've compiled that package, and we've posted that package online so we can reduce the setup of intersecting with a quantum system and make it easy. The second thing that we've done is we've worked with IBM's Qiskit, and we've produced what we call a Dell runtime. So this is Qiskit Dell runtime. And this allows us to look at classical quantum bundles and orchestrate that entire event. So it allows us to look down into the quantum system and to say, now we want to orchestrate this event and push it over here to a physical quantum processing unit, or over here to a virtual quantum processing unit. It also allows you to go out to edge, if that's where you require to go, or up onto a public cloud platform as well. And then the final thing is we built intelligence actually into the orchestration engine itself. This is really a machine learning classification model that we've built in, where we can actually, excuse me, look at utilizing learning to predict the kind of runtime needed. So if that's DRAM, if that's vQPUs, if that's GPUs, and then execute the event against the resources that it needs, and then fine-tune those resources as it goes. So when we look at industry, if we go back to 2021, we had 50 qubits. If we go back a little bit further than that, like I mentioned earlier on, we had 7 or 8 qubits. As of last week, we now are in a world where we're heading well into the thousands of qubits. And as I said earlier on, this is really, really good news for anybody who's interested in working on quantum systems. At an industry level, this is very telling. Most of the figures that you're seeing up here are in their millions. You look at Austria, they're 127 million. Look at Taiwan, 282 million. India are at 1 billion. Germany, where are they? Are pretty high. They're at 3.1 billion. The rest of Europe is only slightly above that. It's at 4.1 billion. If you look over here to that green area, China are at 15 billion and rising. This is what they are doing in terms of investment into quantum architecture. And it tells a very, very clear story around, when we look at the semiconductor space, when we look at geopolitical landscapes, it tells its own story about, certainly where China's focus is, and the US, I know, are ramping up in this area as well. Now, based on what I've told you earlier on in this region, there's certainly huge amount of interest. As I said, I traveled quite a bit and spent 3 trips with a meaningful period of time sitting with customers in the region talking about how they can actually invest in quantum systems. Really quickly and really succinctly, this is the ecosystem. So if you look at, we've broken it really into 4 areas: the execution layer, the middleware layer, the frameworks that you can use, and then the cloud services you can bounce onto. So from an execution layer, you can see them all here. Of course, we're in there. A partner that we do a lot of work with, IonQ, sit in this space. As we start moving up the stack, I mentioned Qiskit, IBM's framework. Microsoft are in there with Azure doing a whole lot of work. And as we go up, we can see, familiar faces. We can see frameworks, TensorFlow, PyTorch, PennyLane, AWS have built a framework. And then interesting ones up the top from a cloud services perspective, particularly Honeywell, who you may not have expected to be in that space. They absolutely are. So, from a quantum computing point of view, really there's 2 areas that we focus in on. One is the analog area, where we're interested in annealing, and the other one is gate-based. From a compute point of view, when we flow down into analog, we have our physical machines, we have emulation engines, we have the annealers, of course, and then we're looking into trapped ion qubits using classical hardware to interface with the quantum system. By its own token, when we look down into gate-based, we have simulation engines, of course, we have our specialized classical hardware, of course, we have neural atoms, we have quantum dots, silicon quantum dots, and our focus at Dell is looking at that and also looking at photonics and what's going on in that space. And of course, you have your superconducting qubits versus the trapped ion qubits that I mentioned a little bit earlier on. So this is really about quantum circuits in the sense that a quantum circuit is a list of gates, and you can see them here: quantum gate 0, quantum gate 1, quantum gate 2, quantum gate 3, and you can see their configurations on line 1, 2, 3, and 4. Where this gets really interesting is when we think about superposition, so an atom or a qubit being able to be in 2 states at one time. What we can then start to do is look at what we call circuit cutting, quantum circuit cutting, where we can actually take the configuration and cut it down into its most efficient config. So what does this do? This is looking at the set of gates being presented to you in any given configuration, then being able to do some quantum cutting against that to drive energy down, and furthermore, to drive cost way out of the event. From an annealing perspective, and I spoke a little bit about energy, this is really focused in on being able to get a particle into or as close to its most efficient energy state within a closed system that we've spoken about here today. So we can actually start to look at measuring its minimal or its maximum value, which then allows us to go, as I said earlier on, and compute with a level of efficiency on a quantum system. Our researchers are really, really interested in manipulating, obviously, physical qubits. So when you think about how energy is created, we have an atom that spins, and when we put pressure on the atom, it has a ripple effect, nearly like throwing a stone into a pool. You see the ripple effect going out, and you have electrons starting to emerge. This is how energy is actually created. And what we're trying to do here is manipulate that spin in order to get a level of control over the atoms. I mentioned earlier on the atoms, bouncing around in their configuration, introducing different atoms can be problematic. In this respect, what we're doing is we're trying to actually get control over those atoms within its magnetic field. Without getting into too much detail about that, it's a complex task, and what we do at Dell is build that architecture that I've just taken you through and simplify that, compress that down into a technology stack that we can drop into your ecosystem and then connect, as I said, out to a quantum computer, either on IonQ's architecture or into some other NVIDIA, IBM, our other partners. There are more, but they're the mainstay of partners that we deal with. And I've attempted to simplify it down here. So what you've just looked at on the previous slide, when you take the lid off it, this is kind of how it looks. So these are our Dell computers over here. This is a reference architecture for building a quantum hybrid classical system. And then it can be presented into you in its different configurations. You can have a small configuration, medium configuration, large or extra large configuration. This is what Dell has been doing for decades. We've done it in genome sequencing, we've done it in all areas of life sciences, we've done it in finance, we've done it in healthcare, and we're doing it again in the world of quantum, where we are looking at how we can take the optimal configuration to solve for optimization problems and other quantum opportunities, and do so at your scale. So it's something that you can start at and then scale into. With IonQ that I mentioned earlier on, we have the compute layer, which could sit within your data center. So this is the layer right here. And we're building an orchestration engine that I spoke to you earlier on about, that SDK that we published on the open source platforms, orchestrating an event through Jupyter Notebook and then into something like IBM's Qiskit, and then platforming you or bouncing you over onto an extensible architecture for quantum computing. So this allows you to interface in a simulated way into a quantum system. In this case, in this event, it's IonQ, and then have the architecture over here that your data engineers today fundamentally understand, and where your data scientists fundamentally understand also. So it gives you that gateway into the quantum world. So that's what we can do today. When it gets really, really interesting is when we try to think through what's going to happen tomorrow. So from an AI perspective, everybody's talking about AI, and we're no exception to that. We've been doing a lot of work in AI for the last 15, 20 years. But there's an interesting thing happening. When we look at GPT, when we look at Mistral, when we look at Llama 2 or Llama 3, when we look at all of the large language models, first thing that comes to mind is there's a lot of talk about small language models and multiples of them. When you think about our Strat 6 that I spoke to you earlier on, the first circle over on this side of the slide was Edge. If you speak to McKesson, to IDC, to Gartner, to Forrester, to any of the analysts, they will all tell you that the future workloads, or the workloads of the next generation, are going to be at the edge. It's where the event is happening. It's where the data comes into the ecosystem. Here's the really interesting thing. If we think of that, and then think of artificial intelligence over a 70-year span, we are only at the end of what we call the second wave of AI. So Llama 3, Mistral, GPT 3.5, 4, going into 5, all built, they're transformer architectures, but they're all built on neural networks. Input layer, output layer, hidden layer. Now, the algorithms that have been blended to build those technologies are the same algorithms that our data scientists fundamentally have been working with for years, in the sense that they're natural language processing algorithms. The third wave of AI are going to have smarter, better, more accurate, and quicker algorithms in the mathematical space and should be able to shape and reshape as they land into the data event ecosystem. So as we land an AI capability down into a factory, into a hospital, into an ICU, into a patient, as we actually get an AI to traverse across the anatomy of a patient to examine its internal organs or its vital statistics physically, that technology, those algorithms, these models will be able to change and shape themselves based on the data and information and metadata that's being presented to it at any given time. So the model, from an AI perspective, is going to be capable of all possible combinations and configurations. So when we think of AI and what we've spoken about today in terms of superposition and entanglement and all of the functions and features of quantum architectures, they're both intersecting. They're both being designed and maturing and evolving in a similar way. They're very, very different technologies, but they're coming together to complement each other. And certainly as a technologist, I see a world where today we have compute, network, and storage, classical architecture, and then we have traditional applications, even if those traditional applications are cloud-native applications. In the future, there will be a world where we will have quantum accelerators at the hardware layer and AI at the application layer as a cognitive application. And we have to be able to build for that. So from an orchestration perspective, we're writing a lot into the classical quantum or classical computing space. We're looking at intelligent quantum circuit transpilation that I mentioned earlier on. We're looking at circuit resource prediction. We're looking at blending AI with quantum today, so we can facilitate for where the architecture is taking us tomorrow. So we see things like resource predictions for quantum tasks coming into metadata, like I mentioned a few moments ago, into the quantum circuit cutting events that I mentioned a few moments ago, into CPU execution times, into how we handle the energy efficiency around annealers for executions, in and around the memory usage of AI events. So from a scheduling point of view, we will be able to have a circuit resource prediction which will allow us to say the data or quantum information is potentially coming in through these different circuits. We're scheduling now in an automated way, in an autonomic way, to say that not only are we orchestrating this, but we're pushing it to the right circuit for the right piece of data, information, and executing against that optimally. That really takes us into this whole idea of transpilation, which is around the circuit frameworks that I spoke a little earlier on, and being able to have each quantum system support a different set of those gates based on its configuration. There are a number of different things that we still have to solve for in the quantum space. There's energy. That's going to help if we get it right. But there's also error correction. So classical computing is far better than quantum computing, funnily enough, at error correction. And it's getting better, but this is something as well that our researchers are looking at, where we're looking at how we handle diffusion models as a potential solution to solve for error correction in the quantum space. I mentioned photonics a little bit earlier on. This leans into it a little bit as we look away from the quantum computing and go down into actually the quantum network space. This really is an architecture which is called PDNNs, or pluggable diffractive neural networks. So these are neural networks that are intelligent enough to understand the information that's passing through those red, blue, and green gates, and being able to classify that information and then hold that configuration so you don't have to shut it down and power it back up again. So today, this is what we're doing. We're looking at light coming in through the system, looking at stuff like fashion and handwritten digital examples, and then being able to share that information from frame to frame, and then classify that information using AI, and then reapply the correct plane without having to shut it down. We're also interested in where silicon is going and where quantum is going. So if you think of all of the domains and all of the algorithms and all of the software we've just spoken about, and you think about putting that into a heterogeneous control engine, this is the future of where computing technology is actually taking us. What we're looking at here is a domain-specific silicon on chip. So imagine having a die, a chip with an Atom processor, with an NVIDIA GPU, with an Intel CPU and GPU, and potentially even with a virtual QPU sitting on that one die. This will solve for a lot of our problems going forward, and it's what the ERI, or the Electronic Resurgence Initiative, is really, really all about. It's about increasing information across the tightest, densest compute architecture that you can bring to the table, and overcome some of the things around microelectronics. So some of the offloading problems that we have with classical computing. If we get this right, we believe that this is going to completely overhaul and revolutionize compute architecture. When you think of von Neumann's architecture, it's that passing of information from one system to another system. This will solve for that, because all of the chips and systems, operating systems, will be sitting on that one die. So you'll be able to connect to a public cloud, you will be able to connect to an edge architecture, and you'll be able to take the right silicon with the right data on that silicon and the right frameworks and governance and compliance and controls and policy, and be able to do that in a streamlined way. So we talked about the first, second, and third wave of AI from a GPU, or from a compute perspective. This is kind of how it's lining up. Another technology that we're interested in and that we're doing a lot of research on is neuromorphic architecture, which takes the whole concept of the control plane and the data plane and bringing the data subsystem up into the memory using technology called memristors. In the context of AI, very, very, very interesting. When you take that with AI and blend it with quantum systems, extraordinarily powerful and extraordinarily interesting. So looking forward, we see a world where, I guess, there's going to be a lot of AI techniques. We see them emerging already, agentic techniques, mapping to things like retrieval augmented generation of models and data into models. And we see these already joining the limelight. Joining in with these approaches, we're going to see AI evolve. So we're going to see algorithms appear that are in the neuroevolution space, that are much more biological by nature, and are much more akin to what we started out trying to build when we started out 70 years ago trying to build for AI. We're going to see AI and potentially quantum turning up at edge in robotics, driving autonomy across these architectures. We're also going to see it turn up in finance and in healthcare specifically, solving, as I said, those optimization problems. Scale has never been more important. And as I mentioned earlier on with the classical architecture, AI and HPC are going to overlap more and more, and we're going to see that as nearly one deliverable, where we have the HPC powering the AI with that blend of quantum sitting in behind it. So we're going to have distributed architectures that I started the talk with. We're going to have near ephemeral, consistent cloud systems, public clouds, private clouds, hybrid clouds, and edge clouds, what we're calling cloudlets. And we're going to have that wave 3 of artificial intelligence come into that ecosystem. We're going to have more data to manage, which is going to be extraordinarily difficult for us to do. We're already living in a world of digital twins where we're not just twinning a construct like a factory or a robot in a factory, but we're actually twinning what we call digital threads, and we're also looking into processes and processes and simulating them as well. Imagine that ecosystem and then introducing quantum technologies into it. Blockchain will rise again through the lens of, we believe, digital ledgers. It's already doing so in many, many places. Composable infrastructure, like I tapped into a few moments ago, is also going to emerge, and quantum is going to take us into places that we've never been able to go to before. Right across our own ecosystems, it's going to help drive exploration into space and answer those universal questions. Control, trust, and responsibility around all of this is absolutely top of mind. We want a demographic with artificial intelligence and quantum computing where that ecosystem is shared and control of it is in the hands of the right people. So that's me for today. I'm around for the rest of the day. Again, I'd like to thank the Foundation for inviting me to talk here. There was a lot to unpack in that session. But I would just leave you by saying thank you for spending the time with me, and take care.